covered already like today, right? Like, so, I mean, this is the benefit of like having these block lectures. We started with simple linear models, right? And now we're already like at how can we interpret neural networks, right? At least like to a certain extent, right? So when we talk about neural networks, I think by now everybody is like super familiar with DNNs, right? Like, so we've seen them a ton and so on. So I don't think I need to give like a lengthy introduction to that. But the big issue that they have to this day still, they're considered like, to a degree at least, black boxes, right? So because of this amazing ability of like extracting features and so on internally, right? That kind of makes them so powerful, but at the same time, it's hard for us to understand what these abstracted features actually are, right? And make them interpretable and understandable for us. And that's basically kind of like the challenge here. So if you want to make sense of it, of course, we can do something model agnostic, right? Because we mentioned we can do this on any model, so we can also do it on DNNs. But something like surrogate models, LIME or SHAP, right, will be like problematic because, again, the main reason why they're so powerful is because they basically learn their own features. And now we're trying to make sense of like limited hand design features in this case, right? And that's not necessarily going to work well here. That's the first thing, right? And also like SHAP is like expensive and so on. So we need special methods to interpret those, like in particular these like extracted features, like the hidden states or the latent states, right? And the second thing is also that commonly DNNs are trained through like, or MLPs are trained through backpropagation. So the question is if we can actually somehow leverage the gradient there and make sense of the gradient, right? So those are two alternative or two perspectives that we have to consider when talking about neural network interpretation. So what new features do DNNs actually learn, right? So imagine we have our little like network here, and then we have like our input, and we know so far we've only looked at like this input features and the outcome, right? So like this whatever height, width, these kind of things, right? But now we kind of want to abstract like, okay, what actually happens if we propagate through the network, right? So what happens at this stage? So what are the values, or like what are the features learned in this hidden layer, right? So, and we can maybe do this by looking at the activation functions, right? So activation functions are kind of, or can be interpreted as like something that triggers that neuron, right? So something that like whatever the neuron got caused it to fire or not, right? So maybe we can see like, okay, what actually makes this neuron fire, right? So what actually like is like causing this activation? And by doing this, by maximizing the inputs with respect to individual, like not individual neurons necessarily, but to a subset of neurons, we'll talk about this in a second, but to individual scopes of the hidden states, right? We kind of like get this so-called feature visualizations, and maybe you've seen them already, right? So like in this case, that won't be anything new. If you don't know what feature visualizations are, be ready to have nightmares tonight. Right? So, okay, feature visualizations. So what do? It's basically an optimization problem again, right? So we want to see basically something has supposed to fire, so we want to maximize the activation of a neuron or the whole layer or like a subset of layers, right? These kind of things. So, but we want to maximize this activation, right, of H. And H can be like a different, could be different. It could be like individual neurons, or we can also think about it as a whole channel, or like the whole layer, like or like the whole hidden vector, or like the output classification layer, right? So it's up to us what we want to look at. But this is something that we want to maximize, right? And we want to like find this X, basically the input now that maximizes that activation. So if we talk about a single neuron, so if we talk about, no, where's my cursor again? Okay. So if we talk, for instance, about this one, right, we kind of want to find the X that goes in here that maximizes that output, that basically maximally fires that activation, right? Or if we want to have like multiple neurons, then basically the sum of it should be maximized.
You couldn't have multiple instances that maximize the activation for a certain.
No, of course it can be. It can be, but we're like, and we might actually end up with multiple examples. That depends on how we optimize it, right? If we look for only one, or if we look for multiple ones, but it could be for complexity, like, right? So depending how deep it is in there, could be multiple instances to maximize that, right? So how do we find our X dash? We could go through all our training data points, right? That's very simple. And just see like, oh, which one, like now for whatever our H is, right? Let's assume a neuron for now or whatever, it doesn't matter. But like, let's say from all the training data set, from the like training images, for instance, or whatever that we've seen, what is the one that maximizes? And let's say this one, right? So this one maximized H. What does it tell us? Does H now maximize for dogs or for cats or for like adorableness or like greenness in the background and so on? We don't really know, right? So with this one, we don't actually know which part of this whole image, right, is responsible for triggering it, right? Because we basically, like in terms of CNNs, we do subsampling, like we basically squish down the image and we look at different aspects of it, right? So like we kind of like in the hidden states at some point, like could be that we only focus on cats' faces, and that's the reason why it's maximized, right, at this stage, just because there's a cat's face available. So that's not the path to go, right? Doesn't make sense to everybody. Okay. So like what we can do instead is we start from noise. We basically actually look at it as an optimization problem, and we say we start with some random X, right? And then we start to tweak that X, and our cost function, so our optimization, is the activation of H, right? So basically like wiggle a little bit here, wiggle a little bit there, and then we end up with something like after multiple steps with something like this. And we know that, okay, this input gives us the maximal firing of H, right? So this is basically the maximum activation that we get. So, and this usually requires some kind of constraint optimization, right? So like only small changes per step, like no sudden steps, right? And like other regularizations to make sure or to be robust against like jittering and rotation and so on. And some projects even leverage like GANs and autoencoders, namely, or like one example would be Nguyen in his 2006 or then 2016, 2017 papers. Okay. So now the question is, what do these features actually look like? And that depends very much on your age, what you select your age to be. And I think the first work that actually analyzed Google LNet and ImageNet. And there we can actually see like, okay, in the early layers, like in the beginning, it seems to be something like edges, right? Like these kind of like things pop up very early on in our hidden states, or like these, they don't pop up. Those images maximize the firing or like the activation of the early layers. Does it make sense? So then later on, we have something like textures, it seems, right? So this would be some interpretation that we have here, right? Oh, welcome back. How's the exam? It was fine. I'm sure you did great. Okay, so we have textures there. Later on, it becomes a bit more complex. We're going towards like patterns, right? So like we abstract from textures to something more structured, even more structured. And then now, like what they coined parts. So this looks a little bit like what we have here, like could be like whole like flowers, right? But like parts of molecules, like some textile, like sheets or whatever, right? Bubbles, like this could be like a console of a car or something in this direction, right? So we have like parts now, and then finally they call it objects, and I call it nightmare fuel. Like so they like something like here, entire eyes, dogs, legs, right? Like these kind of things. So like there seems to be something now with like increasing depth, right? Our abstractions become more object-like, right? Like or like it goes from simple edges to more and more patterns. And that makes sense, right? Because like intuitively, because in the beginning, right? So like we only have like yes and no or like activations on the very early, like is this particular feature existent or not, right? And if it is, if I fire, and then if all of these features actually exist, then maybe I fire because this combination means that this more abstract feature exists, and then like if all of these abstract features exist, then I fire because that means that this pattern exists, and so on, right? So like intuitively, this death kind of perspective kind of makes sense, right? And this is what we basically can see through this optimization, right? And if you want to play around with it a little bit, this is already like older work, but the website is still online and very interactive and a lot of fun. So if you want to play around with it. So the next question is like, we talked about interactions quite a bit today already, right? So can we actually like also see interactions or like visualize interactions or behavior between those neurons. And we can but before that, we need to understand what like the concept of directions in this in this context here, right? So if you have a neural network, like this one, very simple over here, right? Each activation can be considered something like a element in the high dimensional space, right? So let's see, for instance, we have 9 neurons here, right? So we can map this as a nine-dimensional vector, right? And then say like, okay, this second neuron is the second element in this vector, right? And so on. So this neuron would correspond to the 4th element in this vector. And like we can also say, okay, what about, it doesn't have to be only positive values in our direction, we can also go negative. So basically meaning, what if I like subtract whatever activates this value, right? This kind of that kind of perspective here. And then of course we can also now combine them. So we can also say, okay, what happens if I want to look at what activates this and that neuron, right? So this is now a directional vector, and now our H can simply be like whatever, like again, I told you like H can be whatever you want. So, and in this case, we just look at it as the dot product, right, or the linear combination of our directional vector and all the activation that we have, right? So meaning that if we want to have only one neuron, then our D should only have like this one value other than the non-zero in our vector, right? But if I want to have like this entire, let's say, first layer, right, then the first 3 elements should be 1 and the rest should be 0, right? And this is how I can determine now what my H is. Does it make sense? Okay. So with this, we can, for instance, do something like that, right? So we can say, okay, we have these kind of weird visualizations. Where's my cursor again? Right, and here we have like peacock-ish stuff, right? And if we combine them, actually, we see, if we actually want to see what triggers or maximize the activation of those two together, we have these kind of visualization, right? And then the same in this case, right? It seems like the peacocks actually don't matter that much, right? So what does that actually mean for interaction? I will not tell you. So this is like for you to figure out. And in here, for instance, we can see that still like the snake pattern is still dominant, but at the same time, we kind of want to have it in a particular like the structure, a particular orientation or representation here, like in terms of these arcs, right, which we have from this one, and so on, right? Like so. Let's find an example here. So we can even interpolate between activations now, right? Because as I said, it doesn't have to be 0, 1. It can be 0 something. It can be like something more, right? So we can interpolate from like what looks like people to what looks like pictures or the pictures of people, this kind of thing, right? And so if you if you're brave enough, right, so we can interpolate from what could be babies to what can be puppies, which again, nightmare fuel. So don't look at it. If you stare at it too long, it stares back. So don't do. Okay. So that's feature visualization, right? So the advantages is that we get a unique insight into the inner workings of those neural networks, which is great, right? The second thing, like this indicates that there are actually patterns and these more like hierarchical, like kind of like representations inside of neural network, which is really exciting. We can communicate this in a non-technical way, right? So there is no need to understand like, oh, how does like changing this one weight, like or this one value affect the overall prediction of the output? No, we just like show these pictures to people and say like, hey, what do you see, right? That kind of thing. And it can be also still combined with feature attribution, right? And it's like, even though it's most visually in images, obviously, it's not limited to images, right? The big disadvantages are that many feature visualizations are not really that interpretable as we have seen, right? So because like in certain we thought like that makes sense, but it's somewhere like whatever, right? And there is something called the illusion of interpretability. And I mentioned that earlier today already, and that is something really interpretable? Or is it interpretable because we are very good pattern matching machines, right? Like we humans, we are trained to recognize patterns, right, and to like identify and pinpoint them, right? So like I said, like, okay, this is something. And now, but basically what can happen is that you see these kind of images. Again, don't look too close, right? But like, and you say like, oh, but this is clearly a dog, right? Like I recognize this as a dog, but you have to take into consideration that you're a biased like perspective, right? Like you're looking at this because you've seen dogs already and so on, and you want this to resemble a dog. But it can be literally that the only thing that matters is that there is like gray area over here, right? Like or whatever, like that kind of thing. So there's this illusion of interpretability. Is it really interpretable? Like, is this really what is underlying this decision making, or is it what we think underlies that decision making? Does it make sense? That's like an important general like concept in interpretability or in explainable AI, right? So distinguish between, is it really interpretable or do we just believe it is? And overall, if you want to look at like these deep neural networks, right, with billions of parameters, you don't want to look at every single parameter. That's nonsense. So you kind of do this very well. So nonetheless, it's a lot of fun. So I encourage you to go there on your own risk, and you do whatever you want in whatever state you want. So okay, so the next thing, feature visualizations are great, right? Oh, like any questions about that before we go to network dissections?
Yeah, now we've seen feature visualization with image classification models, but how would that look like, for example, with text classification models?
For instance, like if you would to analyze like if you want to have, if you have a classifier that tells you this is a Spanish or like a German sentence or something like this, right? Then you could basically just scramble through your sentences, right? Like mix German language with Spanish and so on, and see basically what activates certain neurons, right? In order to see like, okay, this neuron seems to be responsible to determine the like German teaching or like teaching terms or something like this, right? And this one is like Spanish, like I don't know, food terms or something like this, right? That kind of way. So you could do it this way, for instance, right? Okay. Other questions before we move on? No? Okay, cool. So another approach, right? Instead of looking into the features themselves, we're doing what's called network dissection, right? So feature visualizations aim to visualize the general concepts of the learned features, right? So answering the question, what triggers the particular set of activations? We've just discussed about this at length, right? However, the optimized image, right, are often like much harder to interpret, right? So like that's kind of like the downside that we just discussed. So the idea is, can we actually find concepts that are human understandable, right? And see if these concepts contribute somehow to the overall activation, right? And this is what we call network dissection. So the way that this works is a three-step approach. First, we collect images labeled with human-level concept understanding, right? So for instance, like you have a big data set and somebody went through it and already labeled like, okay, these are stairs, these are desks, those are chairs, these are bottles, right? Like kind of like label that on a pixel level, right? Or like rather on a like area of the image, right? Like, so we have already concepts that we as humans understand, right? And then what we do is we measure the CNN channels activations. So we go through all of the like convolutional layers until the very end, and then usually you have like then some like MOPs or whatever that do the decision based on the vectorized CNN output, right? And we go all the way until there, and that's what we measure as our activation. That's what we care about, right? And then we quantify how well the activations and the label concepts actually align, right? So
actually something different from what is on the slide, because
what?
You said, or rather on the slide, it says like images labeled with human level visual concepts, which I would say is an image with a label, versus what you mentioned with the image segmentation.
No, but you kind of pixel level like labels. Like
Yeah, there is segmentation.
yeah, but that's like that's contradicting, right? Labeling does not mean that you have a single term for the whole image, right? So you literally have like like your image, right? And you have pixel level annotations, right? So this could be class instances. This could be like in this case, concepts, right? So like something like stripes, skyscrapers, or something like this. But this could also be like foreground, background segmentations, all kind of things, like pixel level annotation. Right? Just that in this case, we don't actually need pixel level annotation, but like more like just general areas, right? Where something occurs. So like literally imagine somebody being on this image and like circling something with the concept stairs and then circling something else with the concept like your desks and so on, right? Okay. And then we basically, like at the end, after we have like our activation and so on, we check or we use that measure, right, to check how much the concepts overlap with whatever triggers the activation of those layers, right? Does this make sense? So let's go step by step. The first thing is to collect the data set. And luckily, other people already did the work, right? So there's like several data sets. This is one back in the day, used to be one of the biggest ones, the Broden data set, right? So which has more than 60,000 images with pixel level annotations, something like this, for instance, right? So where we have like cars or like we have like skyscrapers or buildings is red in this case, right? So there's like the legend is like over here, right? Marking the road is this kind of like dark magenta-ish kind of thing, right? So somebody already went through this whole thing and did that for you. So that's great, right? So the next thing is measuring the CNN channel activations of those images. And the way that we do this, again, is that we input the image, right? And we train it and go all the way through until the last layer for the classification. And then in order to basically project this back, right, we basically can like undo, let's say, the CNN, let's say, right, with the activation only the concept that we care about. So what we do is basically for each image in the dataset XD, right, we evaluate our trained model. Again, FHAT always refers to the complex model that we have that we want to analyze and record the activation of like AK, right, like the channel K, right, and we compute overall the distribution of pixel activations. Why do we use the distribution here? Because we kind of want to be more robust towards outliers. So what we do is we determine the 0.995 quantile here, right? Why that particular quantile? Because empirically, the people that suggested this work just had the best results with this kind of like value, right? So there's like, yeah. So but the idea is that only 0.5% of all activations are actually greater than this activation, right? And then for each image in the data set, we kind of like scale it back up and create a binary mask to see where this was active and where it wasn't active, right? So this leaves us with like a bunch of binary masks here. This will be in the Kronecker delta or like the indicator function, right? And then finally, we quantify how well the activations actually label these concepts. And do we do this by computing basically the intersection over unity? So basically saying that, okay, if we have our mask and we have our label concept, right? What is the intersection, right, between those? And what is the unity between them, right? And if we kind of want to maximize this, the higher this is, the more our concepts occur in this image or in this activation, right? So the more confident we are that this concept actually triggered that activation, right? Does it make sense? And again, like some threshold here, some that worked empirically for the people that suggested this work as 0.04 for whatever reason. Like, don't ask me. Like, data evaluations, right? Yeah. But the idea is basically something could be something like this, right? So that you basically have now, oh, you don't see my cursor. You have like some area which is the highest active area in the image, right? Which would just be like the dog face, right? In this case. And like, but the human said like, oh, actually like this whole thing tells me it's a dog. Where in this case, I would actually be even more strict on the side of the machine than the human, but that's what you have, right? And then basically the intersection over union tells you now if the face is like or like this concept, right? Let's say like dog face concept is a relevant concept for the activation of these channels or not, right? So, and this basically is the entire 3-step approach. So what does this look like actually in practice? So we have the concept of heads here in AlexNet that we can clearly see, right? Where it seems that there is like plenty of overlap, right? But also like things were identified, like for instance, castles, like this would be another concept that people like manually annotated in the data set and then figured out that this would maximize the channels, right? And also things like lamps or stairways in this case, right? So this gives you a little bit more of a human level interpretation. So the advantages is that it automatically links like the activations to understandable concepts, understandable human concepts, right? It usually goes beyond what the classification task in itself does, right? Because those are now like provided by humans, and it allows still to do that. But the disadvantages are that you require these giant data sets and this manual labeling, which is very painful to do. So that's a problem, right? And it does only align human concepts with positive annotation, with positive activation. So if something is very negative, we cannot say that like this neuron actually triggers if there is like no stairways like here, right? That's not in the capability of this model, right? And for more details, again, the blog post of this work. And with this, we are done for today. So we would like to do a last 5 and 5, and then that's it. Okay. Any questions before we do the 5 and 5? Okay, then let's do the 5 and 5.